All right, today we're cracking open the Mathematician's Toolkit to talk about one of the most powerful tools inside, functions. Honestly, they're the language we use to describe pretty much everything, to model patterns, and really to make sense of the world around us. So here's the game plan. We're going to start with the absolute basics. What even is a function? Then we'll get into the two main flavors, how we actually write them down, and check out some really cool specialized functions. And we'll wrap it all up by talking about why any of this actually matters.
Okay, first things first, let's get right to the heart of it. Before we start using this tool, we've got to know what it is. So, what exactly is a function?
And to get our heads around that, let's start with a bigger question. What's one of the most fundamental rules in all of math? Well, it really all boils down to defining relationships that are clear and totally unambiguous.
And that leads us straight to our definition. A function is just a rule that connects a bunch of inputs, we call that the domain, to a bunch of possible outcomes, that's the range. Think of it like a vending machine. Your domain is all the buttons you can press, like A1, B2, C3. The range is all the snacks inside. But here's the one unbreakable rule. For every single input, you can only get one specific output. You press B2, you get the chips. Every single time.
And you know what's really amazing? This entire breakdown we're doing, from these basic ideas to all the complex stuff we're going to get into, it's all based on this single page of handwritten notes. It's just a perfect reminder of how powerful ideas can be packed into a simple, clear structure. Okay, so now that we've got the basics down, let's explore the two main families of functions. You can think of these as the two biggest categories in the entire toolkit, algebraic and transcendental. So algebraic functions are built using all the tools you're familiar with from arithmetic, adding, subtracting, multiplying, all that good stuff. It's kind of like building with regular Lego bricks. You can see exactly how all the pieces snap together. But transcendental functions, like the name says, they transcend all that simple stuff. They describe these fundamental patterns in the universe that you just can't build with those basic arithmetic bricks.
So check this out. This is a classic algebraic function. It's a polynomial, and you can see it's made entirely from those simple steps. You take your input, x, and you do a few basic things to it. You square it, you multiply it, you subtract from it. No magic, no mystery.
But then you have something like y equals sine of x, and this is transcendental. You can't just build this with simple pluses and minuses. This thing describes the fundamental shape of a wave, a pattern that shows up everywhere, from light and sound to the tides in the ocean. It's so elemental, it needs its own special definition.
All right, let's switch gears a little. We're going to move from what a function is made of to how we actually write its rule down. And that gives us our next two big categories, explicit and implicit.
So an explicit function is basically a super clear recipe. It says y equals this exact set of instructions you perform on x. An implicit function? Well, it's more like a puzzle. The relationship between x and y is all mixed up together, and sometimes you have to do some work to figure it out. In an explicit function like this one, the recipe for y couldn't be clearer. It's simple. Take your x, multiply it by 2, add 5, and boom, that's your y. It's a direct path from input to output.
Now have a look at this implicit one. It doesn't give you a direct recipe for y at all. Instead, it describes a relationship. It just states a fact. Any point xy that makes this equation true is on a perfect circle that has a radius of 5. It defines the shape by stating a rule that both variables have to follow together.
All right, now we get to the really cool stuff, the specialist tools in our kit. These are the functions designed for more complex, real-world jobs where the standard tools just aren't quite enough.
We're going to look at three of them. Parametric functions, which are amazing for describing motion, piecewise functions for when the rules of the game change midway through, and composite functions, which are kind of like functions working together on an assembly line.
So with parametric functions, both x and y are actually being controlled by a totally different variable, t. And you can just think of t as time. So as time t moves forward, these two equations trace out the path of a point. And this isn't just some abstract idea. This is literally how animators make characters move across a screen, or how GPS tracks your car on a map. Piecewise functions are awesome. They've got this sort of split personality. They play by a different set of rules depending on what the input is. Think about your cell phone plan. You might pay one flat rate for the first 10 gigs of data, but then a totally different, way higher rate for every gig you use after that. That pricing system, that's a piecewise function in the real world.
And finally, we have composite functions. These really are like a little assembly line.
You take an input, x, and you feed it into the first function, g. Then you take whatever comes out and immediately feed that result into the second function, f. This is perfect for modeling processes that have multiple steps, like, say, converting dollars to euros, then taking that euro amount and figuring out what it's worth in yen.
So, we've got this incredible, diverse toolkit of functions. But why does any of this matter outside of a math class? What's the big takeaway here?
Well, it matters, because this toolkit is literally the language of science, technology, and finance. I mean, everything from calculating a rocket's flight path, to creating mind-blowing computer graphics, to predicting the stock market, or even understanding how diseases spread. Functions are how we take the messy, complicated real world and translate it into a language we can actually work with, analyze, and understand. So I'm going to leave you with this final thought. The curve of a ball thrown through the air, the interest growing in your bank account, even the way a light bulb slowly dims, every single one of those things can be described with the functions we've talked about. So the real question is, what part of your world could be described by a function?